Hey, how's everybody doing? Welcome back to Math for Healthcare video lecture series. We're going to continue on with exponential functions here. We saw one video already that's kind of quick and dirty of exponential functions and about them. Here we're going to dive in a little bit deeper. I just wanted to mention a couple things here. One is, why are we interested in exponential functions? For healthcare, well, it turns out that the way drugs leave the body over time is similar to how populations grow, which is exponentially. Okay, that now exponential could be exponential growth or exponential decay, and we'll see a couple examples of each today. I want to remind you that linear functions are characterized by a constant rate of change, and this is so we could compare and contrast, right? That constant rate of change is the slope. What that means is, right, whether x changes from 1 to 2 or it changes from 500 to 501, it's still the function increases by the same amount. And we'll see that this is different with exponential functions, and we did see it in the last video, really. Exponential, to recall, is kind of what we did. We talked about it with pennies, right? But the same exact problem in terms of cell population would be considering how population cells may be changing if each cell divides into 2 cells every hour. So that's exactly our function for how much money Carl would give to Alice from the last video, which was g of t, where t is in hours, is equal to the t. And that's if we start with one cell. Keep it simple. Okay? And that's just a reminder. And we also saw last time, what is it essentially about exponential functions? Well, they're characterized by a constant percent change. All right, as we saw with Alice, Carl and Alice, as well as with this bacteria here, or the cells here, all right? Oh, well, t changes from 0 to 1. G changes from 1 to 2. Okay, so an increase of 1. Whereas when t changes from 3 to 4, we go from, the function grows from 8 to 16. Okay, so a difference of 8. So that increases, so it's doubling here, it's doubling, or 100%, it's increasing by 100% every hour. That's really what that's saying. Okay, so let's look at an example here. And before we start this one, I want to first do, a single cell divides into 2 cells approximately every, let's say for now, let's cross out that 20 because it's a little complicated, and we'll do every minute, okay, in the right conditions. If a petri dish contains 100 cells of E. coli, all right, let's not worry about this last part. What we want to answer is find a function f that gives cell population after t minutes. Okay. Now, notice this is, okay, cell divides into 2 cells, so it means that they are doubling, or another way to say that is they are increasing by 100% every hour. The population increases by 100% of what's there every hour. Now, here, though, we have to be careful because at t equal to 0, notice we have 100 cells, okay? And when t equals 1, we're going to have, it's going to double, 200. 2, it's going to double again, 400. 3, it's going to double again, that's 800. And I could continue on. And hopefully we see this is similar to the situation with Carl and Alice, the pennies. Uh, except for now, instead of starting with 1 penny, we're starting with 100 cells. All right, so recalling that anything raised to 0 is 1, we remind ourselves of our formula. I'm going to write down here y equals y naught, that's initial amount, which in this case is 100, times 1 plus r, the rate. R is 1 here because it's 100%, all raised to the t. So here we get a function f of t equal to our initial amount, 100 cells, and our r is 1, so we get 2 raised to the t. Okay, and in my lower left screen here, that's what that looks like. That's pretty extreme, that's steep, that's going up. Probably not realistic, but that's a reminder. Now, let's go back and say, well, what about if I wanted to do now every 20 minutes? Okay, let's think about that. Let's make a chart, still starting with 100 cells. Let's first make a chart to see when we get to 400 cells. Okay, so t, and then I'm going to call this function g of t. All right, just to be different. We know at 0 we have 100. And then I'm going to skip some now because it's every 20 minutes. So after 20 minutes, then I have 200 cells. And after 40 minutes, there I have 400 cells. And that's how we could answer that question. Now, what's the function g of t here? This is a little more complicated, but let's think about it for a second. Well, hopefully I can convince you that we still have the initial value 100. Okay, it's still doubling, but now it's every 20 minutes. So we want our exponent to go up by 1 every 20 minutes. The way we do that is we make this t over 20. And you could check that. Just look at it. What happens? Okay, t equal to 0. That's 2 to the 0, which is 1. We have 100. That's good. Notice, and over here, I'll plug that function into Desmos, and we could check our values. But thinking about how it's working in the exponent, right? T has to get all the way to 20 until I'm raising 2 to the first in g of x. Okay, but g of 20, all right, 200. And let's see if our, after 60 minutes, well, our table tells us we should have 800. Let's check that. G of 60 is 800. Now, I do want you to notice that the steepness does change with that, all right? But they both go through the point 0, 100. Okay. Now, that's a little tricky how we get that in there. And we'll learn some more systems. We'll get some more practice with that. All right. Okay, so let's look at another one here. Now we have a car that's worth $10,000, and that on average, cars depreciated in value about 18% per year. Find an equation modeling the price of your car as a function of time t in years. All right, so first of all, we see it's depreciating. That means that we need a function. Let's come up with a function. We'll say let h of t be car's value after t years. Okay. That what? The higher t gets, the lower the value should be. So instead of like our other two, exponential functions, I'll get rid of one of them so there's less on the screen, is we want something that's going to decrease, right? It's going to go downhill from left to right. Now, one way to say that here is 18% is our, it's kind of like our 100% was before, but now it's our decay rate, which means that our, from our formula, let me write that down again, y equal to y naught times 1 plus r raised to the t. Okay. Well, r here is a negative value, negative 18, because it's depreciating. Here, r equals negative 0.18. I also want to say, I'm going to go back up and say h of t be car's value after t years in thousands of dollars. So I don't have to go in and you put all those zeros in. All right, so if our r is negative 0.18, what's our initial value? Here it's 10, which really means $10,000. Now, using our formula, we get that h of t equals 10 times 0.82, because 1 minus 0.18 raised to the t. All right, let's see what that looks like. Okay, so that's going downhill from left to right. And sorry, my mouse is acting up a little bit there. Let's go 25 years out. Okay, so see, it's getting close. It's getting real close to zero after 20 years, but it's never going to get less than zero. And in fact, it never hits zero. Okay, but that is, and notice now here, this is a decreasing function, and this is called exponential decay. And I want to note that how can I use this function? Oh, okay, what's the value after 15 years? So plug in 15. And by the way, that says 0.5, but really, remember, because we're in thousands of dollars, that is $509.57 about. Okay, that's after 15 years. Obviously, this thing's not a Toyota. But that's the exponential decay. Now we could sum it up a little bit over here in our next slide. And then we'll take a break and I'll do another video. All right. So in general, the relationships exhibiting exponential growth or decay have equations of this form: y equal to f of t, p naught is our initial quantity like we saw, 1 plus r, where r is the rate. If it's an increasing rate, it's positive. If it's a decay rate, it's negative. Okay, and that should generally be a decimal. Okay, it's a percentage, so generally that's a decimal, somewhere between 0 and 1. And r is the percent change per compounding period. If r is greater than 0, we have exponential growth, like we saw our blue function there. It was our g of x was increasing from left to right. That's some exponential growth. And then if r is less than 0, we have exponential decay, or it's a decreasing function. Okay. And notice that corresponds. If r is greater than 0, then the base of our exponential function is greater than 1. And if r is less than 0, it's between 0 and 1. Okay. Notice you can't decrease by more than 100%. That's impossible. You can increase by more, but you can't decrease by more. K. Now, so notice we've kind of slipped this K in up here. Well, that's kind of like our first problem, although we divided by it because it was only once every 20 minutes. But K is the number of compounding periods per unit of time. So maybe and T is your time in your chosen unit. So let me say, for instance, something like G of T equal to 10 times 1.2 to the, let's say 20t, where t is in minutes. Okay. What this is, okay, let's see. We got r greater than 0, our base is greater than 1. We have exponential growth here. Now our k is 20, so that means that this growth happens 20 times every minute. All right, it's kind of the opposite of what we saw in the beginning one. And that's what we mean by k. All right, thanks for listening. Why don't you try a few problems, think about these, and I'll have another video ready for you shortly. Enjoy.